I got applause for a moment. This afternoon's session will now be on finding planets, and our first speaker is Angie Wolfgang. Please, Angie, take it away.
Thank you. Right, so I was tasked today with overviewing transit surveys for habitable planets. So this has been, the question of habitability and also transit surveys have been touched on in both Jesse and Jason's talk. So I hope to give you guys a little bit different things to think about. So just to remind ourselves, the transit method is when we have a planet crossing the face of the star, and then if we observe continually brightness of that star, we see a dip. And the depth of that dip is proportional to the area of the planet divided by the area of the star. And so if we observe the star long enough, over a long enough time, observational baseline, and we see multiple of these dips, then we can figure out what the orbital period of that planet is. And from the depth of the dip, and knowing that that is proportional to the ratio of areas, then we can get out the planet radius. So I'm putting this up on the title slide because I'm going to come back to this at the very end, particularly how transit surveys assess whether or not a planet is habitable. So keep this in mind. Right now we're considering orbital period and planet radius. So first of all, so Jason just gave a great talk about the radial velocity method and some of the excitements and challenges of finding habitable planets with that method. So why do we want to do this with transits, other than just finding more habitable planets? Well, actually to date, it is the most prolific planet detection method, especially for small planets, possibly terrestrial. There's some inference that has to happen to go from size to composition, and smaller planets. So if we just take a look at the raw counts of confirmed planets, okay, so I'm going to refer back to this distinction a little bit later. Confirmed planet is one in which you found this dip, this transit signal, and you've gone out and gotten additional observations of that star planet system in order to rule out other explanations for dips that might look similar, for the transit method at least. And so here, this is on the NASA Exoplanet Archive. We see that the number of confirmed exoplanets here far outweighs the rest, all of the other planet detection methods combined. This is interesting and it's possible, first of all, because photometry, that process of just measuring a star's brightness over time, is much better suited to large surveys than spectroscopy is. And spectroscopy forms the basis of radial velocity imaging, for example. Also, to compare it more to the RV planet detecting method, Jason talked at length about how it's really hard to figure out what's going on the surface, the dermatology of the star. I love that, Jason. That is still a factor for transits, but it confuses the signal a little bit less. This dip is a little bit more distinctive from the other kind of stellar noise photometrically that's happening on the surface of stars than this kind of longer term orbital variation that we see with the radial velocity method. So stellar noise is still a factor, but it's less of one. Also, we have the current instrumentation that we need in order to get signals that are, in order to be able to observe signals that are small. We can get the precision that we need, which is not currently the case for imaging, or astrometry, at least for the very small planets. Also, transits repeat, so we can study these planets in detail. That's an issue with microlensing. Microlensing is a one and done kind of thing. Also, many planets exist in multiple planet systems. This is one of the really cool things that we found with the Kepler results. It's just the prevalence of multi-planet systems. And so, because of that, it is, okay, so as you have more planets in the system, you need to take more observations in order to distinguish them with radial velocities. And so when you look in bulk at how long it takes to kind of tease apart a multi-planet system, it's more straightforward with transits. And you can detect atmospheres when the planets are in transit. So if you detect a transiting planet and you're able to get precise enough observations while that planet is in transit over wavelength, then you can get a sense for what its spectrum is. So there's a lot of exciting things about transits. I'm going to come back to why it is not the only way that we're searching for habitable planets and how it's complementary, very synergistic with RVs. Okay, another reason why transits is that we have many more detections to look forward to. So what I'm showing you here is kind of the arc of all of the NASA missions that are related to exoplanets, both from the past looking towards the future. So kind of narrowing it down here just to transits, we have which missions were involved in detecting transiting planets. In the past, we have Kepler and Corot. Currently now-ish, it's TESS and Chaos. And then farther in the future, we have Plato, which is going to be thanks to our European colleagues. In terms of atmospheres, we have even more data to look forward to. So in the past/now-ish, is Hubble and Spitzer. Then in the future, near future, we have JWST. And in the further future, we have possibly the Origin Space Telescope. So these 3 telescopes plus an X-ray telescope are being adjudicated basically for in this decadal survey, and which one is going to be recommended in the survey. Before moving on, I also want to say, looking into the future, direct imaging is also very exciting for habitable planets. We're not quite at, technologically, we're not at the point where we can detect the atmospheres of small planets using direct imaging, but we're doing this for supergiant planets, and people are actively and very hard working to get the instrumentation down to the level that we need in order to be able to do atmospheres, find atmospheres around more habitable planets. Okay, so far, what is our census of habitable planets? I find it highly amusing that both Jason and I performed the same exact experiment of Googling this, and we found 2 completely different websites that catalog what the habitable planets are. So this is the Habitable Planet Catalog. So here, oh, by the way, this couple dozen planets were identified with the following criteria. First of all, there are radii between 0.5 to 1.5 times the radius of Earth, and the stellar flux that is incident on the planet, the insolation flux, is between 1/4 and 1.6 times the insolation flux on Earth from the sun. So these here at the bottom are the transiting planets. So I'm going to just overview a couple of these transiting systems that are very exciting and spark a lot of press and a lot of excitement. And hopefully SETI is targeting these, these planets as well. Okay, so first of all, Kepler 62 and Kepler 186. So just to get a sense for what these systems are like, I'm showing the inner solar system here to scale. All right, so we have the Sun, Mercury, Venus, Earth, Mars. And then the habitable zone, so this is determined by insolation flux and the modeling that Jim Casting described earlier today, is the kind of faint green region here. Also, not only are the orbits going to be to scale, but also the sizes of the planets here to scale, although they're not in scale to each other, obviously. Okay, so the Kepler 62 system here, we have planets that are, first of all, it's a 5-planet system, and we have planets here that are on average larger than the terrestrial planets in our own solar system. They're also more tightly packed, they're closer to their stars, and the star, Kepler 62, is 4 times less luminous than the sun, all right? So it's a cooler, smaller, less luminous star. All right, Kepler-186 is even smaller than both of these. So again, I put this to scale. So the habitable zone for this system spans basically the orbit of Mercury here. And it's only the outermost planet in that system that is habitable. So this is a very tightly packed system. So these are examples of the kinds of systems that we weren't sure existed before Kepler. This is one of the things that was just completely outstanding and phenomenal about the results coming from Kepler, is the existence of these systems. Okay, and the star itself, Kepler-186, is 20 times now less luminous than the sun. So this is another representation of the graph that Jason showed with the size of the star versus distance from the star in which the habitable zone exists. So we have a larger, brighter star, very small, cooler star, habitable zone is closer in. Okay, another really exciting system that has a habitable zone planet is TRAPPIST-1. Now, TRAPPIST-1, it is a transiting detection, but it's a completely separate mission, and it's ground-based. So this telescope particularly targets very, very small stars, almost not stars. And so this system is so exciting, by the way. It's gotten so much press that it actually has its own website, which is pretty cool. So you can go to this website and kind of look at the story for how this planetary system was discovered and studied. And obviously, a lot of stuff is still going on now. Okay, so here is the TRAPPIST-1 system. So we have the distances to the size of the objects are not to scale, but within the scale, the distances between things and the sizes between things are to scale. So we have the star, and then there are 7 planets in this system. Jesse mentioned this system earlier today. Now, this system is so compact that comparing it to our own the inner solar system is not a good analogy. Instead, a good analogy is comparing it to the Galilean moons of Jupiter. And so we can start to see here just how diverse and extraordinary these habitable zone planets can be. Oh, right, and to get back to this point, so TRAPPIST is such a small star, it's so faint, it's actually 2,000 times less luminous than the sun. Okay, so I showed you 3 exciting examples of planets that are in the habitable zones. They happen to be in multiplanet systems, so that bodes well for analogies to our own solar system. But they are not analogies to our own solar system in one crucial way, because the stars themselves are so dim. So why is that? Right, so we have the sun and we have TRAPPIST-1 here to scale. That's not actually, this is actually an image of the sun. This is not, that's an artist's rendition. Okay, so because of the sizes of these 2 stars vary so much, the transit signature actually, for the TRAPPIST system, it is boosted based on, compared to the solar system planets. So if you think not just about the pure size of the planets, but the amount of area that the planets are blocking from the star, so in other words, the depth of the transit, you can see here that the transit signatures for the TRAPPIST planets are whopping signatures, especially compared to the transit signatures of the terrestrial planets in our solar system. In particular, the depths are pretty much equal to the ones of the gas giants in our own solar system. And so this is an observational bias, right? So it's a lot easier to find transiting planets around smaller stars, and those also happen to be dimmer. So we really want to find a true Earth analog, right? One that is at the right distance from its star to have liquid water on its surface, that is the right size, small, it could be terrestrial, but then also one that orbits a star like the sun, right? So this is really hard to do because these habitable zone planets around sun-like stars have much smaller transit signals, which also means that they're harder to confirm. And so really what's possible with these kind of detections is more of a statistical estimate of the rate of habitable planets. Okay, so as of the last catalog to come out of Kepler, these are all of the potential planets that are close to or in the habitable zone. So the habitable zone is outlined by these two lines here, the inner edge and the outer edge. The y-axis is the effective temperature of the star. So we can see that there's a wider range here of potential unconfirmed planets in terms of stellar effective temperature. The size of the dot corresponds to the size of the planet, and then the color of the dot corresponds to how secure of a detection it is. Yeah, I gotcha. This is an important distinction because, for example, these planets are not as secure detections as the ones that are darker here. So in order to really understand what the rate of habitable zone planets there are in our galaxy, we also have to account for this uncertainty on whether or not that planet is actually there. These planets don't have follow-up observations to confirm their planetary nature. And so if we compare what we do have here with the number of stars around which we should have found one of these kinds of planets, plus factoring in the likelihood of whether or not these planets exist, then we can get something like a habitable planet rate, okay? And right now, this rate is all over the place. It's dominated by systematics. So here we have an estimate of the rate here. This is the habitable planet rate in some units that I don't want to go into. And then we have probability density, right? So this is a probabilistic statistical estimate. So this has this question of how often habitable zone planets occur around stars, sparked an enormous and rich literature where people made different choices about what kinds of planets to include, what kind of stars to include, how exactly to do the D-bias correction that John Chambers talked about. And all of these things, all of these choices actually produce very different results. And so this is this shows you the range of results here. This is from Chris Burke's paper from several years ago now. One of the issues here is defining what the habitable zone actually is. So we heard a little bit of that from Jim Casting earlier today. There was, in fact, a study analysis group that tried to synthesize this literature in order to, and corrects for all of these different choices to the best of their ability in order to kind of try to arrive at an average kind of value for this. So they found that about 60% of stars have habitable planets. But the jury is still out, so there are several works still being done right now that look at this issue with both the latest data and also improved methods. And so this is one from Penn State, Danley Su. He looked at this using approximate Bayesian computation, which is one way to account for these systematics that fixes one of the issues that produce a wide range of systematics. Anyway, so jury is still out, but it's probably somewhere in the tens of percent. All right, so note also that, so I've been talking a lot about Kepler data, and we heard a lot about this from Jesse this morning too. The reason why I'm still talking about Kepler data is that, so the arc of missions that we have to look forward to, TESS is happening now, but it's targeting much shorter period planets. So we're only going to be able to find habitable planets around more small stars with those, because those are much closer in, their orbital periods are smaller, and so you can find them with a shorter observational baseline. Plato, farther in the future, sometime in the next decade, may or may not probe the habitable zone. They're still deciding on what exactly observational cadence they're going to use, and those choices are going to affect whether or not they can get anywhere close to the habitable zone. So Kepler is going to remain the premier data set for understanding the rate of habitable planets for a long time into the future. Also, before I'm done here, I want to just make a note that habitability is complicated, right? So on my title slide, I showed that transits give us a planetary radius and the orbital period. Those are the two things in which we have been using to define all of these occurrence rate habitable estimates here. But there's a lot more that goes into it. Okay, so this is from Vicki Meadows and Rory Barnes's paper, overview really, of everything that really should be considered in order to identify a planet as definitely habitable. And so far what I've been talking about are just these three things on this plot. So the picture is a lot more complicated. They've also broken it down in terms of whether or not it's easy to obtain these quantities. Maybe perhaps easy is green, perhaps a little bit harder to do. You need to do a little bit more modeling, get more difficult observations. And red as in there is still a lot that we do not understand, even on the theoretical side, about what's happening there. So there's this issue of habitability is complicated. And there's going to be a lot of work being done on it in the future. But one thing that we can do that just takes one step beyond what I've been talking about here is instead of just thinking about planet radius, also think about planet mass. And mass and radius give us a sense of bulk density, which we can then get a sense for what the composition is. So this is shown here by this plot. So we have planet radius and mass. Right, so before we were just thinking about radius, but if we incorporate mass and we include models of what the interior structures of these planets are, so those are the solid lines here, we can get a sense for, based on where the planet masses and radii fall, what kind of composition they can have. This is the kind of thing that I have actually been working on a lot in order to take the data and infer the compositions from them. And so this is just one example from several years ago now of doing this in order to understand the fraction of a planet that is gaseous, essentially, as a function of its radius. So this is the next closest step that we can do in order to understand the habitability of planets, and in order to get those masses, we need radial velocities, because transit just does not get that for us for the vast majority of cases. So to summarize, with long enough observational baselines and high enough precision, transit surveys can yield many planets at the right size and the right stellar installation. But because of observational biases, pretty much all of the habitable planets that we have found in terms of the right size are around smaller, dimmer, and cooler stars than the sun. Statistical estimate, perhaps 10, 20, 30, maybe 60%, but there's still a lot of work that needs to be done there, and habitability is really complicated. So I want to come back to Jason's suggestion at the beginning of his talk about perhaps the detection of extraterrestrial intelligence will actually help us with this idea of habitability, because it'll help us identify which planets are inhabited, and therefore we can backtrack and understand what the conditions are of that planet compared to ones that don't have these signatures. Thank you. Yeah.
Thank you. A very nice talk, Angie. Wonderful summary, but I want to take issue with your table at the very beginning where you listed all the confirmed planets by the different methods.
Okay.
You listed astrometry as having one confirmed planet. That's not quite the case. It's claimed by the Palomar tested interferometer of a wobble, an interferometric wobble in a binary system that's consistent with a Jupiter-based object around one of them. They don't know which one it is. These are early type bright stars, and there was no way to do a follow-up on it. So it's unfortunately an interesting claim, but that's not one that can be confirmed. But if you stay tuned for my talk on Tuesday, I will show a system that possibly could be confirmed.
Okay, exciting. Thank you for yeah,
I was
Jesse.
going to say, those numbers are from the Exoplanet Archive, which that's my data. And all that means is someone in the referee literature got it past the referee that there's a planet by astrometry.
Yeah, it's
Regardless of whether you believe it.
It's
someone
been published.
believed
In fact, I'm going to go off on the paper. So yeah, it did slip by me.
Felicia.
So I saw an interesting talk by Kevin Schlafman recently, where he's also trying to infer the hydrogen fraction that might be around in terrestrial planet atmospheres, and claimed that if you take all of the low precision data, including upper limits that exists, you do find a higher fraction of small planets with hydrogen and helium envelopes.
A higher.
Have you seen it? More small planets actually do have hydrogen and helium envelopes, which he used to imply that they had to form earlier when there was still more.
Oh, I see. I should. I went to grad school with Kevin, so
you should
we should talk.
Yeah. So I was just wondering if you had seen that or had any comment on how much the upper limits at the low. So essentially, what low density planets get used in that analysis?
Yeah, thank you. So I was going to say this at the beginning of my talk, but I just jumped right in. I'm actually an astrostatistician kind of person, and so my expertise is really in the statistical modeling itself. And so Alicia has really hit on the point that I hold near and dear to my heart about upper limits being extremely important and very informative, especially when you consider them in a population sense. And so now with the Gaia stellar parameters, so the result that I flashed up before from several years ago, that was before any of the Gaia stuff came out. And so now with the Gaia stellar parameters being able to decrease the uncertainties on the radius of the planets, plus we have more radial velocity estimates. First of all, compared to what I showed, there are more planets that have more well-constrained bulk densities, but then also there are just more planets that have more informative upper limits. And so, yes, the upper limits are important even with Gaia. The upper limits are important, especially when you're considering going from a sample size of 200, which is what I use, to the entire Kepler sample. The upper limits are very important. So thanks for bringing my attention to that. I'll have to send Kevin an email so we can.
One last question.
Just a small point, maybe my own ignorance, but I'm wondering if you're asking for a false positive on that last point, because if I were an extraterrestrial civilization, I might want to broadcast from a quieter location, like the moon or a planet, out as my broadcast station and not my home. And so therefore, if you're focusing on where the signal's coming from, you may be in the wrong place.
All right. Well then.
That's some like Nash game theory.
Thank you.
Very much, Angie. Our next speaker is Ruslan Belikov, and he will be telling us about imaging habitable planets.
While this is being set up, I just want to say thank you for inviting me, and I'm absolutely thrilled to be at the Greenback Observatory for the first time and to interact with colleagues I don't often interact with. SETI holds a special place in my heart, even though I don't directly work on SETI. And because this is a diverse professional community, my talk is going to be a very, very high-level overview. So the people here who work directly on exoplanets might know everything, but hopefully this will be useful to a lot of you. So I will talk about direct imaging of habitable exoplanets and searching for evidence on life, of life on them. Before I start talking about direct imaging of planets, let me first highlight the the methods that are responsible for most of the planet detections to date. And so these have been discussed already by Angie, Jesse, and others. Alan will talk about astrometry in a later talk. And so these methods have been responsible for driving the exoplanet revolution and the explosion, and as Jesse said, the exponential Moore's law or Mamajak's law of exoplanets. They have been indirect methods, so the data from them looks like this. And over the past 10 years, standing on the shoulders of these, if you will, a new method has been coming onto its own, which is direct imaging. And direct imaging is just what it sounds like, taking a picture of exoplanets. And this is what the data from direct imaging looks like. So these are some of the most famous directly imaged planets or planetary systems, and it's a time lapse. You can see the dates taking off here, and planets orbiting their stars. One point I'd like to make with these is that, so first of all, the star is blocked, and if the star wasn't blocked, you wouldn't see anything there except for the star. These planets are very far away from their star by our standards. So here, for example, is our Earth orbit as it would be at that distance for scale. Also, these planets are very bright compared to the Earth. They're many orders of magnitude brighter than our Earth would be relative to the Sun. So imagine having a little blip here. That's an Earth. That's 1,000 or 10,000 times dimmer than that, and that's the problem we're trying to solve. Now, technology to do this already exists or almost exists in the lab, but not yet on telescopes. So, what does an Earth look like from far away? Here's one example. And by the way, the Sun is so bright compared to the Earth. It's 10 billion times brighter. Even if you block it with Saturn, you still have a lot of solar light left over, and you can barely see our planet right there. If you zoom in on it, it's showing clearly. You can even make out a moon. But this is what it looks like from within our solar system. This is an actual image taken by the Cassini mission. But we're going to be looking at, if we're talking about looking for extrasolar planets, we are looking at them from much, much farther away. And so even if you look at it much closer than another star, this is an image taken by the Voyager mission at the behest of Carl Sagan, just as the Voyager mission was exiting the solar system or close to. And it looks like a pale blue dot. And many of us remember Carl's words that everyone that you've ever known, every old wars and every thought that anyone has ever had or any human has ever had is all contained on this pale blue dot, a mote of dust suspended in a sunbeam. So what we're trying to do now is to get a second pale blue dot image like that of another Earth orbiting another star. And here's a simulation of what such a planet could look like with one mission concept I've been involved in around Alpha Centauri. And by the way, here's a Venus twin. And so you could get images like, so imagine having an iconic image or a second iconic image like that of another Earth. By the way, when I speak of imaging these planets, I don't mean imaging continents and resolving oceans. We just get an unresolved dot. Just like we can't resolve stars, we can't resolve planets as well. And in fact, the actual planet size on that image is there. You see the little Earth there? I mean, you can hardly see. So the point is that with foreseeable technology, we're not going to be resolving continents and oceans on these planets. We'll just get an unresolved dot. However, the significance of that dot is that we can do spectroscopy on it. And we can, for example, if we take a spectrum of that dot, we can differentiate a Venus from Mars and from Earth. And so these are simulated spectra of Venus, Mars, and Earth. And so on Earth, you can see there's all sorts of biomarkers, oxygen, hydrogen, and on Mars and Venus, you can't really see them. And detecting oxygen and water is, of course, strongly suggestive of life. There are lots of arguments about how suggestive it is. There are a lot of abiotic ways of producing oxygen. This is a very high-level overview. This slide, by itself, and this question deserves its own talk or its own workshop, in fact. And actually, I think the same is true about most slides in this talk, so it's very high-level. But regardless of what you think about how strong of an evidence detecting oxygen or methane or whatever is of life, I think all of us can agree that a spectrum of a planet is a major piece of evidence for the case of life. So it's very important to get these spectra. And direct imaging could get us spectra of planets. Transits, by the way, can also get us spectra and have gotten us spectra of planets. But the sensitivity of transits drops off very quickly for potentially habitable planets, especially for potentially habitable planets around sun-like stars. And I think Jim mentioned this point. Only one Earth orbiting a sun-like star out of 200 transits its sun-like star. So if the question that you're trying to answer is, how many of the nearest 200 potentially habitable planets are habitable, then transits will give you an answer for one out of those 200 planets. And direct imaging will be able to give you an answer for all of those planets. So now let me talk about technologies for how to block the star so you can see a planet. That's the main technological challenge in this. And there are two technologies, the coronagraph and a star shade. So let me show you first how a coronagraph works. And a coronagraph is a technology to block the star inside the telescope. And you can see as starlight enters the telescope, you use, so this is the Airy pattern point spread function of a star, and you can use a series of masks, and exactly what kinds of masks you use and where you place them depends on the style of the coronagraph, but all of them use some masks to block the star, but not block the planet, which is this blue beam going to your camera. So, but when you block things like that, you get an image like this, which is scattered light from the star, because you always have imperfections in your telescope. Even if the telescope is in space, and if the telescope is not in space, you get these imperfections from the atmosphere. So you have to use adaptive optics or deformable mirror to remove these aberrations from the atmosphere or from your telescope, revealing the planets that are in your image. So that's how a coronagraph works. And so this historically has been the first method people worked on to remove, to see things around stars. Another method that has been getting attention is the star shade. And the way that a star shade works is it just blocks a star outside your telescope. So you need to have anything fancy inside your telescope, but you do have to build this amazing but expensive thing and fly it hundreds or 50,000 kilometers away from your telescope. So there's a trade. These techniques are complementary. They're both being developed, and they both have regimes where they're useful. In fact, some missions use both of them. Angie showed this slide already. I have a slightly edited version of the slide. And so I want to switch gears and talk about missions to directly image habitable planets. And so this shows NASA missions, European missions, space missions, ground-based. Some of them are concepts, some of them are flying. One thing that you may note is that, and Angie did a good job kind of talking about it, is that currently we have a big wave of exoplanet transits. So I'm sure that will continue, as well as RV and hopefully astrometry as well. But if you look at the next decade or two, there seems to be a possible big wave, maybe even a likely big wave, of direct imaging missions and concepts, and on the ground as well. And a lot of these can do potentially habitable planets. So the ones that are definitely designed to do potentially habitable planets are LUVOIR and HEBEX, which are NASA's flagship mission concepts for the 2030s. But there are a few that may, if we're lucky, get us images of our pale blue dot. So I'll talk about these in a little bit, both from from space and from the ground. So for the rest of my talk, I'll briefly mention the capabilities of all of these things, which are summarized in this plot. So this plot shows potential. So if every star had an Earth twin, then this is where they would be on a star-to-planet brightness ratio and separation from the star plot. So for example, Alpha Cen, if there was an Earth twin around Alpha Cen A, it would appear 10 to the 10 times dimmer than its star and at about 1 arcsecond or 0.9 arcseconds. The capability of existing instruments and existing direct images is here. And I'm mixing apples and oranges a little bit here because these are self-luminous planets and these are reflected light planets, but bear with me for a moment. So this is basically what we can do with current technology. We're pushing down in this direction with technology advancements. And so space-based telescopes have this regime, and ground-based giant telescopes, like 30-meter class telescopes, fall into this regime. So red color here is Earth twins around M dwarfs, hypothetical Earth twins around M dwarfs, and yellow is around sun-like stars. So you can see sun-like stars, Earth is 10 billion times dimmer than the star. Around M dwarfs, it's more like 10 million or 100 million. So ground-based telescopes are pretty good at detecting Earth twins around M dwarfs. But you need space telescopes to detect Earth twins around sun-like stars and FGK stars. Also, depending on how large your telescope is, you can access different numbers of stars at different distances. You might be surprised to learn that in order to detect an Earth twin around Alpha Centauri, a 30 to 45 centimeter telescope is sufficient, provided that it has a powerful enough coronagraph. Then a 1 to 2.4 meter telescope is sufficient to access dozens of stars. WFIRST is 2.4 meters, and it's not quite designed to get down to 10 to the 10 contrasts, but I'll tell you a little bit about that and what we can do in the next slide or next 2 slides. Everyone is looking forward to HEBEX and LUVOIR, which will break open the piñata of exoplanet detections or exoplanet images over here. Shameless plug for a mission that I proposed with a very talented team called Alpha Centauri Exoplanet Satellite, which is a 45 centimeter telescope to directly image capable of directly imaging Earth twins around Alpha Centauri A and B. So it's a 45 centimeter small explorer mission. And unfortunately it wasn't selected, but Kepler also was not selected 4 times, so we keep advancing the technology. And it generated interest from the private sector. There's a mission concept called Project Blue that is trying to do similar things and trying to privately. Going to larger telescope, and by the way, there are also EXO-C and EXO-S mission concepts that are $1 billion in cost, 1 meter to 1.4 meters, and they would be able to detect potentially habitable planets also. Going larger in size, the WFIRST mission, so this is probably the most real concept out of the space ones that I've mentioned. It's a general purpose telescope designed to do dark energy, but also exoplanets, 2.4 meters like Hubble, with a coronagraphic instrument if it doesn't get canceled. Launch in the mid-20s, possibility of a star shade later on. WFIRST is not designed to detect potentially habitable planets. And its requirement is 10 to the 7, 10 to the 8 contrast as you can see here. Its projected performance is a little bit better, 10 to the 9 or so. This is, official W1st slide projected performance. And an Earth at 10 parsecs appears here, so you might say, okay, W1st just is too far from being able to detect potentially habitable planets. And you'd be right for all stars except for Alpha Centauri. In fact, anything you know about exoplanet detection, Alpha Centauri probably breaks that. So, if you look at Alpha Centauri b, which is a K-dwarf, there the contrast is not 10 to the 10, it's 3 times 10 to the minus 10. And in gibbous phase, it's 10 to the minus 9, which brings a gibbous phase Earth twin around Alpha Centauri b within the range of detection of W1st. Now, before you go out and tell everyone that, oh, Russ told me that W1st can detect Earths, we need a lot of luck. First, CGI needs to not be canceled. Second, it needs to be able to handle binaries. We're actually charged to explore that question. And a potentially habitable planet has to exist around Alpha Cent b in the first place. Not much we can do about that, but Jesse told us that chances are between 10% and 100%, which I think are pretty good odds if we're talking about something as significant as another image of a potentially habitable planet. And the things that would truly blow this out of the water are LUVOIR and HEVEX, but we have to wait till the 2030s to do that. They are really the missions that will definitively tell us if life is common or not by imaging dozens or hundreds of stars and look for potential signatures of life biomarkers on planets around them. Let me also mention ground-based concepts. So the NEAR project is looking at Alpha Centauri in thermal infrared 10 microns, trying to detect planets there that way. And they are trying to get down to 2 Earth radius. And they're planning a publication in October, so look for that. They might be able to detect something. You can also detect Earth twins with extremely large telescopes, which are being planned for the mid-2020s, around M-dwarfs in reflected near-infrared light, as I showed in one of the slides earlier. And they can also do sun-like stars in thermal infrared at 10 microns. Thermal infrared isn't going to give you a pale blue dot, but it will give you a direct image, a complementary direct image to the pale blue dot, which we want as many images, as much data as we want. All of these things are complementary. So to conclude, exo-Earth imaging is within reach around Alpha Centauri and M-dwarfs within a decade, and around other stars within 2 decades. Remote detection of life is possible through spectroscopic biomarkers, which is essentially measuring the next factor in the Drake equation. And chronographs and star shades are key enabling technologies. As a last thought, I'd like to also overlay a thought about why we do this. And I think in this audience, we all get shivers down our spine whenever we think about finding life on other exoplanets. So we don't need any reason beyond that. But something that Martine said struck me, which is this is really inspiring. And a lot of us were inspired by Apollo 11. And that's part of why we do this, is because it was so inspiring. So I think that detecting another Earth, or detecting life on another Earth, is the Apollo 11 of our generation, or maybe of the next generation. It could be just as inspiring for the next generation as Apollo 11 was for us. So just wanted to end on that thought. Thank you very much.
You didn't say anything about interferometry.
Yes, so thank you for letting me know. Yes, there's not currently an interferometry project I know that is at the same development level as the concepts that I showed. There was the TPFI concept, of course, and the Darwin concept. Those were very nice interferometry concepts, but for one reason or another, they are not sadly currently being pursued. I hope that in some point in the future, we will have an interferometer in space taking data in infrared on the planets that are discovered. But currently I'm not aware, but correct me if I'm wrong, I'm not aware of any interferometry concepts.
There's a ground-based program called the Planet Formation Imager that is just a nascent concept to do, infrared and detect planets as they're being born. But again, that requires money.
Yes. Jim?
Russ, you mentioned HabEx, which is a 4-meter telescope, and LoopWire A it is, which is
Yes.
a 15-meter. There is a LoopWire B, which is an 8-meter, which actually may be the sweet spot for...
Yeah, you're right. So I should have included that. I agree that is probably the sweet spot.
Could you say a few things about the difference between transit spectroscopy,
Yes.
able to detect biosignatures,
Yes.
versus this is reflection, right? So there's a slight difference between the transit spectroscopy and the spectroscopy.
Yeah, correct.
that you're
Well,
talking
so you could do a reflection with transit spectroscopy if you do like secondary transits and not primary transits. But you're right. With transits, you're generally talking about looking through the upper layers of the atmosphere, whereas with direct imaging, you're talking about looking at the double pass through the entire atmosphere and the surface.
Yeah.
So I think that the double pass through the atmosphere plus the surface could give you more information.
Could. Not will give you?
Yes, well,
But, back to what Natasha Batalha, she was not here yet, but at her PhD defense, we asked her if you had an Earth twin around TRAPPIST-1, what could you see with JWST? She's been working on detectors for that. She'd do a straight line across the blackboard with a little dip at 2.2 microns, which is the CO2 band. Unless things have improved since then, you really can't characterize an Earth-like planet with transit spectroscopy with JW.
yes. So, I mean, it's hard to compare how much more you can push transit spectroscopy and how much you can push, direct imaging. And if you throw equal amounts of money at both, what kind of data you would get. But generally speaking, at a high qualitative level, I agree with that.
Afraid we're going to have to pass on at that point, but thank you very much. And we pass on to Meredith McGregor to tell us about habitability of our nearest neighbour.
Or unless it's infrared. Yeah, you can.
Okay, great. I'm excited to give my talk to this booming thunderstorm around us. So I decided to change my title slightly. It says I'm talking about the habitability of Proxima Centauri b, but I'm really only talking about a small piece of habitability. So I decided to change it to the origin and impact of flares in the Proxima Centauri system, because I'm not going to be talking about atmospheric modeling or planets themselves, but simply about the star and its activity. So we're going to specify. And before I launch too far into this, I just want to take a moment to thank all of my collaborators on this project. So I'm going to be showing some new work at the end, which is part of this very large project that I've been working on with Alicia and this whole team of people. None of this would be possible without all of their contributions and hard work. Okay, so why would we care about stellar flares? I like this figure from Tom Barkley at NASA Goddard. Flares have the potential to both modify, ionize, and erode a planet's atmosphere over time. This can include photo dissociation of molecules, notably water and ozone. So here we have our lovely flare and a CME. A CME is a coronal mass ejection. I should say, like any good astronomer, I tend to slip into jargon sometimes. So for those of you who are not astronomers, please stop me if it gets confusing. So stars are active, right? Our sun is active. It produces flares. They're associated with coronal mass ejections. And then these streams of high energy X-ray and UV photons and then energetic particles go and hit our Earth's atmosphere. We're nicely protected by our magnetic field and our atmosphere. But we can imagine the scenario around other stars that have exoplanets around them. So, M-dwarfs, which is what I'm going to focus on today, are kind of the favored targets of many of our upcoming and current exoplanet missions. I'm sure we've all heard much about M-dwarfs today. Notably, M-dwarfs, while they are lovely for finding exoplanets in the habitable zone, also are known to have much stellar activity. So orders of magnitude more activity than our own sun. So this is showing habitable zones for 3 different stars. And the sun-like star is the middle case. Cooler stars like M-dwarfs have much smaller habitable zones, so this is nice because it makes it easier to find a planet in a habitable zone because it's orbiting much more quickly, so we can catch many more transits or radio velocities. But it also means that that planet is much closer to its star, so if that star chooses to erupt with some charged particles, many more of those are going to hit that planet. Okay, and my last slide of basic intro here to get us all on the same page of stellar flares. Flares produce emission across the entire electromagnetic spectrum. So sometimes we just think of flares as maybe optical light, but actually flares produce everything from very long radio wavelength emission all the way to the X-rays. So this is sort of a toy model of what we think might be going on during a flare, and the basic idea is that you have magnetic field lines that have foot points on the surface of the star, and these foot points are moving around, and so the magnetic field lines twist up, and eventually they break. And as they break, you produce this sort of cascade of emission that is everything from the radio waves down to the X-rays and gamma rays. These are a lovely picture. This is one flare from our own sun, the star that we can study the best. We can actually image these flares. And this is only a very short wavelength range. It's 131 angstroms to 1600 angstroms. And you can see this flare looks totally different in every single one of these wavelength bands. So to emphasize, no single wavelength is going to give us a complete picture of what's going on with a stellar flare. We need to actually look across the entire electromagnetic spectrum to really kind of understand what the energy budgets are and what that means in terms of exoplanet habitability. So I've been focusing on the Proxima Centauri system, which we've heard in passing, but just so we all know exactly what Proxima Centauri is, it's an M5.5 star. It's our closest M star at 1.3 parsecs. And it has this wonderful planet, Proxima Centauri b, which is thought to be in the habitable zone. It has an MP Sinai of 1.3 Earth masses, and it's at 0.05 AU. And I sort of came into this work because I, as Alicia showed, hopefully typically work on circumstellar disks. And so there was a paper that came out at the end of 2017 claiming the system of circumstellar disks in Proxima Centauri. So there were a system of 3 dust belts kind of surrounding the star and the planet. And these dust belts were claimed from Alma observations. So I'm going to drill down on this in a second, but essentially there were actually 15 different observations taken with the Alma telescope looking at Proxima Centauri. And then in the original paper, all of this work was sort of summed together to make one image of the star and these kind of possible dust belts. We've already talked quite a bit about Alma, so I can be brief, but I wanted to emphasize that for this, it's important to know that Alma actually has 2 sort of arrays to it. It has what we call the main array, which is these 50 12-meter telescopes that can span these ginormous baselines to 16 kilometers. It also has what we call the Atacama compact array, which is 12 smaller 7-meter antennas, and these are sort of closely packed together. And you can use both of these arrays separately or together. So the observations that were taken in 2017 actually were 2 observations with the full 12-meter array, and then 13 observations taken with this Atacama compact array. All of the observations that I'm going to show today were taken at 1.3 millimeters. If you like frequency space, that's 230 gigahertz. That's what we call band 6 with Alma. And Alma doesn't observe at a single frequency. It observes at what we call a bandwidth, which is a range of frequencies. So you get 8 gigahertz total of bandwidth. And you observe in these 2 linear polarizations, the XX and YY polarization. And I'm going to flop back and forth between some jargon here. With Alma, we typically call an observation a scheduling block, or an SB. So some of these figures will show the label SB, so you know what that is. Each of these is about an hour and a half in length, and then during that hour and a half, the telescope basically looks at your source for 6.5 minutes, and then it looks at a calibrator, and then it comes back to your source, it goes back to a calibrator, and it does that for the entire observation. Okay, so without further ado, some data. So what I'm showing here are 3 images. These are from the 2 observations that were taken with the 12-meter array with Alma. On the left is all of the data combined together, and then each of the 2 observations separate. And then the fluxes are at the bottom here, so this is just kind of the total amount of flux in the image measured in this little point source. So there's some variation, they're fairly consistent. The expected photospheric flux, if this was just a star behaving like a normal quiet star, is 74 microjansky, so these are a little bit in excess, but not by a huge amount. And we can also actually go through and make a light curve where we look at each of those 6.5-minute integrations separately. So these are now plotting those individual integrations. And there's some variation, not a huge amount. We can... Boom! So on my next slide, it would have been perfect. We can argue that this slight excess might actually be due to sort of a continual small flaring from the stars. So stars can have big flares, but they can actually have this sort of continual sort of small rumbling, like the low-level thunder we're hearing. Not the big boom, but the little thunder, right? So you can actually produce sort of a general excess in luminary wavelengths just from this sort of small flaring. Okay, we can also get big flares. So this is now looking at the ACA observation. So that's that compact array. Again, all of the data averaged on the left, and then the first 12 observations in the middle, and the last observation, the 13th observation, all by itself on the right. And as you can see, we detect a nice point source in the combined average data. We detect basically nothing above a 3 sigma significance in the middle image, and we detect this huge bright point source in the last image. So that's a little bit puzzling. You can actually split that now down into not even just the integration times, but basically the dump time of the correlator, which is a few seconds with Alma. And you see that all of this signal, which was then averaged with 9 hours of noise to make this image, is actually this significant flaring effect, which is where I want my big boom, where the star is basically non-detectable, and then there's a series of small pre-flares, and then a giant flare in which the star brightens by a factor of 1,000 before decaying back down in a period of about 2 minutes. So it's pretty dramatic. So what does this mean? Unfortunately, this is very bad news for dust in the system, because if all of your nice point source is actually due to the star having a massive flaring event, you can basically rule out all of the dust emission in the system. So I'll do my favorite hobby horse here, just to say that I think we really need to better understand what the stars are doing at millimeter wavelengths in order to start characterizing these unresolved warm dust belts. But excitingly, this means great things for stellar activity and stellar flares and habitability of exoplanets. So we never actually, before this, detected millimeter emission from a stellar flare. So this is kind of an entirely new observational window for us. So a few general properties. At its peak, the flare is 1,000 times brighter than during quiescence. If you compare that to solar flares, which we've detected a handful of in millimeter wavelengths, it's 10 times brighter than the brightest solar flare we've ever seen in a millimeter. And we can now look at not only the flux as a function of time, but we can use the properties of Alma, the fact that it observes at this 8 gigahertz bandwidth and also has 2 linear polarizations, to start getting at some other properties of the flaring emission. So this is showing the spectral index, which is just how the flux changes as a function of frequency. And you can see that as you go into the flare, the spectral index becomes steeply negative and then recovers back to what we'd expect for a Rayleigh-Jeans tail as you sort of come out of the tail of the flare. And then in the bottom panel, I'm showing a lower limit on the linear polarization. So polarization, for those of you who are not astronomers, is basically telling us what direction the light waves are actually traveling. And we can see that the polarization actually changes slightly as you go into the peak of the flare. So obviously, it's hard to say too much from one event. So we're trying to build up a sample. So now we've detected a second flare. So this is another star. So this is Proxima Centauri again on the left. But now on the right, I'm showing data from AU-MIC. So AU-MIC is another M-dwarf star. It's an earlier spectral type. It's an M1. And it's also been studied excessively because it has a lovely debris disk around it. It's one of only a few debris disks we know around an M-type star. And if you dig through the archival Alma data, looking at the debris disk, you'll notice that there's actually a significant flaring event that occurs from AU-MIC as well. The flux scale is a little bit lower here, but the since AUMIC is quite a bit further away, this is actually even 10 times more luminous than the Proxima Centauri flare. So this is an even bigger flare. And it shows very similar properties. So you can see this same kind of dip in the spectral index and then this kind of peak up in the linear polarization. So we think that possibly these millimeter flaring emission is probing an optically thin part of the synchrotron spectrum, which would allow us to actually start saying some things about the electron energies and electron densities, which we can't actually get at other ways. So this seems to be suggesting that the electron energies have to be very high in these flares, and they have to have these sort of high electron densities. And I want to actually, this analysis was done by a summer student of mine last summer. So, great, we have 2 flares. We're building up small number statistics, but we'd ideally like to get many, many more, right? Because I can only argue so much about the physics of stellar flares from 2 events. So what I've been working on with Alicia and this whole team of collaborators is to do this really multi-wavelength study. So between April, and I guess finally ended in July of this year, we carried out this massive campaign to look at Proxima Centauri with about 8 different telescopes for greater than 40 hours on source. The time per telescope varies slightly, but let's say 40 hours on source executed simultaneously between all of these facilities. This was a feat. So we have Alma in the millimeter to try and build up statistics on millimeter flares. We used the DuPont telescope with Carnegie has at Las Campanas to do optical spectroscopy. We used the Everyscope and the Las Cumbres 1-meter telescope to do optical photometry from the ground. We had TESS observing at the same time from space. HST STIS observations to do UV spectroscopy, SWIFT to do UV and X-ray, and then Chandra to do X-ray high-resolution spectroscopy. And so we executed all of these at the same time, along with a complementary Australian effort, which was not perfectly in sync, but sort of on the same days, using, again, ANU 2.3-meter, ADCA, Parks, and the Murchison wide field array. So this is really kind of the first time we've executed such a grand-scale panchromatic analysis of M-dwarf flaring activity. And so what I wanted to do kind of towards the end here is to spend some time showing you highlights of what we have seen from these new observations, which the data analysis is basically ongoing now. We have several summer students who are frantically working away back at Carnegie, and we are still getting data coming down from various telescopes. This is all very preliminary. So I know this is a radio quiet zone, so people can't tweet that much, but please don't tweet anything, because it is not published yet. But I thought this was the right audience to show some things too. So, first of all, multi-wavelength observing campaigns are hard. This is something I learned. So this is my massive table, which I just wanted to show for dramatic effect, which is along the top, telescopes. So we have ground telescopes on the left, and space-based telescopes on the right, and then dates, and then green boxes are days that everything went very smoothly. Red boxes are a combination of either we didn't have time because of scheduling, or something crazy happened, like the Alma correlator shut down, or HST's gyros decided not to function and the telescope turned off. A whole variety of things, but there's a fair number of times where we actually have lots of green, which I consider a major win. So this is kind of the full summary of all the data that we've gotten. And what does that actually show us? So these are a few plots where we've actually started going, so we're still kind of processing all of this data and trying to line up times. But in some places we've been able to get a little bit further than others because some events were particularly bright. So these are 2 events that kind of stuck out in which we've been able to get both the Alma data at the millimeter, the TESS data from TESS sector 11 in the optical, and then HST in the UV. So this happened on April 29th and May 1st. I think they're really cool just to look at because we actually have all these telescopes running at the same time, which is something we've never done before. So there's some interesting things that you can see by eye just looking at these. Both of these HST flares have this sort of double peak structure, and you may look at those and think that I'm totally making this up and they're the same data because they look incredibly similar, but they're actually not. So they have the same double peak structure with this almost exactly the same time separation between the 2 peaks. The Alma data seems to correlate pretty well with the UV data, at least in these 2 flare examples. And the TESS data seems to show the same kind of double peak structure, but sort of offset by some time interval. So there seems to be some time delay between the TESS data and the HST data. So, and I will note also that these Alma flares are incredibly short. So I showed you those flares from Proxima and AUMIC, which are a few minutes in length. These flares are seconds in length, so this flare happens in about 5 seconds, which is kind of mind-blowing that a flare could happen on such a short timescale. So lots of things still to be learned. And of course, these are only the ones that are kind of the lovely highlights where I've combed through more data. One of our summer students has been doing a significant amount of pairing up the TESS and HST data, so this is sort of a collage of things that we see in both, so you can sort of working on cleaning up the TESS data to the kind of maximum cleanliness, but you can kind of see there's peaks that peak up between different things. There's sometimes where we see only one flare, there's kind of these multiple small flares that happen, so there's all sorts of things. So my takeaway from looking at these is that we can't really just consider stellar flares as one population of events and only do statistics for one type of thing, because really there's all sorts of different things going on, and these different kind of groupings of flare structures all have different properties. So I think hopefully this will tell us a lot more interesting things about the physics that are producing flares of different structures at different wavelengths. And then this is sort of an example spectrum taken from the HST sys data. So for all of the HST data, we have not only light curves, but we also have spectrum. So we are working on combing through these, but this is showing you in blue the quiescent spectrum. So this is the stellar spectrum, no flaring emission. And then orange is now overlaid the flaring spectrum from that particularly massive flare that happened on May 1st. So you can see all of these lines, which I've tried to list out at the bottom here, that are sensitive to chromospheric emission and flaring, kind of peak up like crazy during the flaring time, so we can start to actually not only just look at light curves and kind of total flux energy budgets between all these different wavelengths, but actually look at these spectral lines. Okay, and I think I am just about out of time, so I wanted to end with some takeaways. So for our millimeter stellar flares, we, for the first time, detected stellar flares of millimeter wavelengths. This is entirely new, using Alma right now from Proxima Centauri and AUMIC. Millimeter flaring emission, given the fact that we have detected it so nicely and easily in our current campaign and from previous archival data, is probably common. We just have completely missed it until now, which is likely because we don't typically look at our millimeter data on a few second intervals. And excitingly, this opens a whole new observational window on stellar flaring mechanisms that we can use to try and really learn the properties of the atmospheres and the mechanisms that are producing these flares. And then looking at this in a multi-wavelength perspective, no single wavelength is going to give us a complete picture of stellar flaring physics, so we really need this kind of multi-wavelength work. We've now executed this massive 40-hour campaign spanning radio to X-ray wavelengths. So stay tuned for exciting new multi-wavelength results for Proxima Centauri coming soon. And I'll take any questions. Do I found people? Yep.
There is some relation I'm trying to remember between the energy of solar flares and some other variable, and you can actually draw a very nice linear relation or log-log relation for solar to stellar flares. Do you know where Proxima Centauri B's flares fit on that relation?
Are you thinking like Alicia Arnaud's paper on
I can see the figure in my head.
X-ray flux?
X-ray flux versus radio flux?
Yeah, the X-ray flux
is very polymerase.
Yeah, it's
But
something
that
to do
is-
with energy.
There's definitely, people have made many papers trying to correlate the X-ray and radio flux for outdoor flares. Although that seems a little fuzzy.
Well, yeah, and that'll break down possibly with Proxima Centauri.
And we will be able to answer that because we will have X-ray and radio simultaneously, so we can, I don't know
Okay,
which figure
let's-
you're referring
we'll
to,
take
but we
it
can,
Yeah.
if you find it, then
Right,
yes.
fine.
Proxima B, you said the M sin I was 1.3 Earth minutes?
Yes.
Do you know the sin I?
No. So there was a great, lovely moment where everybody thought we had the sign I, because if you actually had detected a debris disk around the star, then if you assume everything is nicely coplanar, then the inclination of the resolved debris disk would give you the inclination of the planet. But
It went away.
I would caution on that because there is no current evidence that there is actually a debris disk in the system. The nice thing about executing 40 hours of Alma observations is that if we account for the star and then sum it all together, we will have the deepest image of the dust around Proxima Centauri possible. So if there is a dust disk there, we should see it. Yes?
So, I mean, that program that you did over 40 hours with the 8 telescopes, that's amazing. What an amazing achievement. So I want to say that first. That's very cool. In the data you showed, there was always a delay between the high energy event happening and the optical counterpart. What's the mechanism by which there's that delay?
Yeah, that is an excellent question, and I don't have a definitive answer at this point in time for you, except to say that if I go all the way back, right? So our general picture of flaring mechanisms is that different wavelengths should trace different parts of the stellar atmosphere, different heights in the stellar atmosphere, and different processes. So in theory, you might expect there to be a delay, and so by measuring that delay, that should be able to help us inform models.
Can we see that in the sun? Like when we look at our sun, is there a delay?
I don't know how much multi-wavelength. Sorry.
It's going big, but that almost looks like somebody said their clock's wrong.
Yeah, but you have an HST test delay. That doesn't make it. They're both optical, right?
The HST is STIS. It's far UV.
Oh.
Yes.
What did the X-ray show?
What did the X-ray show? So that I am still working on the X-ray data. So we have the Swift X-ray data, and we also have UV data from Swift, and then we have the Chandra X-ray data, and we're sort of still getting it all downloaded and processed enough to be able to show it. I will say, these events definitely show this offset. Some of these are sort of are less clear that there is an offset, or that it's in the same direction. Like in this far left one, right? If you call that peak and test the peak, then it's actually only before the HST peak. And in some of them, it looks more like it's almost simultaneous, like in the top left panel. So I would hazard to say that that is maybe real in those two events, and that this is, maybe this is one type of flare, like we get this double peak structure and something is going on that's producing this offset. And in some cases, we get a lot of smaller flares and they're the same and it's a totally different mechanism.
That would be cool.
Which would be cool, right? So the hope is that we can get enough statistics by looking at enough, since this is only a tiny fraction of the data we have, to be able to start getting enough statistics of multi-wavelength flares to say something real about that.
Awesome. What an exciting concept.
I want to make a quick point, which is that you point out that the debris disks, which you said are not there, were discovered by Anglada, who is a Spanish radio astronomer, who is not the same as Guillaume Anglada Escudé, who is an optical astronomer who found Prox Centauri. And Guillaume is from Catalonia, and he's not a Spaniard, so let's be careful.
Okay. Thank you very much, Meredith. Okay, I'm now going to pass over to our self-moderating panel for panel discussion on detecting habitable planets. And everyone is here, so all the way.
When people start getting up and going,
Can we bring up the slides?
Are they on?
So we do want to have this panel discussion. On the other hand, I'm at that phase of life where I don't want to miss any more cocktail hours, and so I'm motivated to get this one finished up soon. I want to start off, though, with just showing a few slides that are basically a reaction to other talks we heard earlier today. And the first one has to do with population synthesis, which is a reaction to the wonderful Kepler data that Jesse showed us, as well as the theoretical models that John Chambers showed us. I want to show you how far away we are from having a really good theoretical model for exoplanet population synthesis. It really is still an Earthshot, I think, for us to achieve that, if not a Moonshot. So if we bring it up,
yeah, what's the file name again? I'm sorry.
panel, it says panel boss.
Okay, yeah. I do. Maybe that's what I'm trying to look at.
Moonshots
I guess exoplanets.
That's the thing, is Earthshot looking for an Earth-like planet? Because that's hard to
No, this
Oh,
month,
yes, I
this
think it
year,
is.
this locator on Earthshots, 3 decades of Moonshots.
Okay, so what I want to show you is some results from two Japanese scientists, Shigeru Ida and Doug Lin, who have spent a lot of time doing very detailed models of core accretion in the same way that John Chambers talked about, not doing full, complete numerical calculations, but taking shortcuts using a few parameters to parameterize what you might think. And they made their predictions for what would be seen in here in 2008. So it was 1 year before Kepler launched and began gathering data. And so what they showed you here is a bunch of results. Where at the top is what was known from previously from basically Doppler detections. So that's the data set they're trying to match. And here's what they came up from their model. They made several different changes in their basic parameters and varied some parameters. And they felt that, some of these do a pretty good job of reproducing that part there. So that looks like success. We understand how planets form. You notice, though, that they also predicted this area here as not having much of anything. And so that's basically, they predicted it should be a desert right below here. Well, then, of course, along came Kepler. And it turns out that same area is actually where most planets are. And so I just want to give it as one example of what the problems can be in trying to explain the known population with a single mechanism. Part of the problem with this core accretion model was that what you end up with is a whole bunch of hot Jupiters because they migrate so quickly, and you end up with nothing in this sort of 1 to 10 to 20 Earth mass area because those all create gas and become gas giants up here. So you can get rid of both of those problems if you have shorter disk lifetimes. But if you have really short disk lifetimes, you cannot make gas giants by core accretion. But if you have short disk lifetimes, you can make gas giants by something called disk instability, which I will actually not talk about in this conference besides that. But it's the end member of having a gas disk be gravitationally stable enough to make gas giants. And I think we know from reality that there are some wide planets that are gas giants that probably are hard to form by core accretion. So you probably need both mechanisms. Just had to get that one in. And then finally, the other one I want to show is in reaction to Jason's talk about exoplanet extreme precision radial velocities. There is a big effort underway right now as a result of the Exoplanet Science Strategy Report that we came out last year, saying that NASA and NSF should get together and figure out a way to actually determine how we can get masses of Earth-sized planets from solar-type stars. Not just M-dwarfs, which we know how to do, but in order to get down to Earth size. And they're shooting not for the 9-centimeter wobble of Earth, but saying let's get to 1 centimeter so we really have good high precision work. So this thing is underway right now, and they're hoping to figure out how to do this. But as Jason said, one of the big problems is not the instrumentation, it's the jitter. And so they've got a real problem ahead of themselves. They think they got $50 million to blow, though. So they're going to spend $50 million trying to figure out if they can solve the stellar jitter problem. So, okay, at this point in time, we get onto the panel. Alicia, would you like to start off saying something in particular about USALT, perhaps?
Yeah, so I just, so this is actually, I wanted to say that in the USALT program, and I think it's actually, there's a lot of interest this week in what's happening, which maybe relates to some of the ethical talks we had earlier today. So the USALT project is the idea that we're not going to solve the biggest problems in astrophysics with a single large telescope located in either the north or the south, that we're going to need a larger complement of instruments and complementary capabilities with 2 telescopes in order to solve our big problems. And one of those big problems, or big questions, is can we detect biosignatures from the atmospheres of Earth-sized, Earth-like planets in the habitable zone around nearby stars? So that is a key question that motivates the construction of the 25 to 30 to 40 meter telescopes that different groups are planning for the ground. And so the National Optical Astronomy Observatory is coordinating an effort between the 2 US-led efforts, which are the 30-meter telescope and the Giant Magellan Telescope, to think about them as a system and to think what can we really do and what instrumentation do we really need to be able to do this really fantastic problem of detecting biosignatures, and particularly the ones we're thinking about are oxygen and methane. And if you're interested in what people are thinking about as the science projects that one might do with those telescopes, there are actually a lot of public white papers that were submitted as a result of a key science project process that was led by the Optical Astronomy Observatory that were submitted to Astro 2020. And so you can find the one on detecting oxygen, you can find the one on advanced instrumentation. There are a whole bunch that came out of that process as we think about a real moonshot to detecting biosignatures. And then, of course, we don't, this week, it's looking a bit tragic for the 30-meter telescope. There are protests by Hawaiians that are blocking the access road to Mauna Kea. So right now, there is actually no observing going on, as far as I know, on Mauna Kea as a result of those protests. So even the great telescopes that we have up there are not currently being used. And if they're successful in continuing to block the road, there will be no 30-meter telescope at Mauna Kea. And it's not clear what the options are if it's not built there. So, I guess we have some thinking to do as a community about where science stands in our list of priorities and understanding the universe stands in our list of priorities that involve, competing social demands from people on Earth. And so there's a lot of ethical discussion happening in the astronomical community, particularly this week, about how we think about that.
Well, their backup site is looking at the old Moonshots in the Canaries, but I guess they haven't said those words because they don't want to give the game away.
I think that's a very pessimistic attitude, and that most people who live in Hawaii anticipated a lot of this and are not surprised by the reaction of the community. The governor is behind the program. I don't think there's any question that the road will be cleared, and will probably be cleared in a matter of days. I think that all of the legal challenges to TMT have gone in the right direction, and it's just a matter of being patient. The process that exists in Hawaii is one of collaboration rather than confrontation, and it's not going to work the same way there that it does in Washington, D.C., on the Mall, or other places. I think that there are a few people in Hawaii that need to make these statements for various reasons related to Hawaiian sovereignty and how the political system works. It's a transient effect. So I wouldn't spread this sort of pessimistic view whether we're going to be able to use TMT on Kea.
So let's be upbeat. At the USELT conference they held in Tucson back in November, the feeling was that in order to build both the GMT and the TMT would be roughly $4 billion. And so the idea was to perhaps get NSF to go in for a 25% share, which means $1 billion. I think Glenn Langston has been at this meeting. Is he still here by any chance, Glenn?
I don't have any opinion. I have no knowledge.
Well, please, carry the water back to headquarters and let them know that, if they weren't already aware of that, which I'm sure they are, that this is a wonderful offer, highly leveraged. 25% share will get you some Nobel Prize quality results, I'm sure.
So, Alicia, is the justification in terms of looking for biosignatures for the two telescopes the fact that they're in the two hemispheres? Is that why? Can you explain more the complementarity in particular about biosignatures?
Yeah, so there's two sets of complementarity. One is that, yes, you just have access to more targets. Proxima Centauri is not going to be available from the north, for example. The other thing is that if you need to get a lot of transits, there's a timing component because they are, so for objects that are equatorial that you can observe from both telescopes, like if you need to do 20 transits of Proxima Centauri and you beat that against when it's nighttime at your telescope and when the weather is good enough at your telescope to do it, then you really win by having two telescopes at different longitudes that can observe your and just accumulate enough transits to get a transit spectroscopy signature faster. And so I think that's a different, qualitative difference, than just saying we get twice the
Is there an equivalent instrument on both for the science that is needed?
Neither telescope really has the appropriate instrument, and so, I think if NSF joins, one of the really exciting possibilities is to bring to fruition the appropriate instrumentation faster than it would probably happen for either telescope.
So it would be a second
alone.
Generation instrument? Okay.
Yeah, so we're thinking in two types of instrumentation. So you could do transit spectroscopy with a single object spectrometer, but the real power will probably be from combining a coronagraph so that you're actually then feeding the whole field of the coronagraph into a spectrometer, so that you win in contrast with the central star, both in terms of the suppression of light from the central star and in terms of the ability to detect the different spectroscopic signature of the planet from the star. And it will be the combination of those two things that probably allows us to do from the ground what otherwise is a contrast that is generally only achievable in direct imaging from space. So that's the idea, and neither telescope has baselined an instrument like that for its first generation.
As Russ pointed out, NASA and JPL in particular have put a lot of effort in developing chronographs for space telescopes, whose basic principles will work for ground-based telescopes as well. And in fact, the Astrobiology Science Strategy Report made an explicit recommendation, since we were charged with both ground and space, made a recommendation that NASA should pursue high contrast imaging from both the ground and space, both near term and more medium term. More far term there was W first, near term was more ground based. And so I actually made a presentation to Thomas Zurbuchen and Paul Hertz, who did not want to hear someone asked them to put money into a ground-based telescope. But I said, listen, it's again leveraging. If you can provide enough money to develop a really nice coronagraph where you already have the technology expertise, then you piggyback on an SF share as well as the private share and do something really wonderful. So we'll see what happens.
So what's better, a 30-meter telescope on the ground with a coronagraph, or an 8-meter telescope, or a 4-meter telescope in space with a coronagraph?
They're not the same thing.
I think we need both if we
Oh,
want to.
no, Russ, no.
I do, you choose.
So that's a question. Do you want to study habitability of Earths around sun-like stars or around M dwarfs? And
So the ground-based one would be involved.
yes, that's the basic complement. I mean, there's overlap, but the basic complementarity is that ground gets you M dwarfs. At least if we're talking reflected light, they can do 10 micron imaging of sun-like Earths around sun-like stars, and then space gets you Earths around sun-like stars.
I think there's this misconception that you can trade a large ground-based telescope for a small space-based telescope and get the same thing. And I think, as Russ has indicated in his talk, and it's going to be talked about on Tuesday, that's just not true. That a lot of the exoplanet study problems are resolution problems. And if you can control the wavefront in the telescope, which means on the ground controlling the atmosphere, and in space it means doing other things, then you'll never match what you can do on the ground, because you're not going to put a 40-meter or a 25 or a 30-meter telescope in space in our lifetimes.
Yeah, so it's a question of what costs less money, developing the technology to do that on the ground or launching a space telescope. At least if we're talking 10 to the 10 contrast,
We're not going to do 10 to the 10 contrast on the ground.
Yes.
But we might do 10 to the -7, and we might do even better than that. And with some processing, we might get close enough to get a little bit beyond what you call the M-dwarf region.
And we will be on Sky first at a certain point.
Jason?
Yes.
So when we think about these big multinational projects, we can think about things like the EHT or LIGO, where they knew what they were looking for and they worked for a long time, and they basically got the result that they're looking for now. They're exploring that result. But there's also projects like the Keck telescope, which were more general purpose, and where I would argue the most amazing results that came out of those telescopes were not in the science plan. Or Hubble would be an even better example, where I'm sure this is the original science plan to look back and kind of chuckle at, so we did some of those things. So when we're talking about hunting for habitable planets with these large, these ELTs, with these space-based missions, where do you see them living on that spectrum? Are there,
That's a huge advantage, I think, for the ground-based telescopes, because you can continuously update their instrumentation to take, so if you imagine a phase space, which is spectral resolution versus wavelength coverage, you can continue to populate that phase space over time, right? And so Keck didn't start with the complement of instruments that it has today. And you're more limited in what you design into a space mission, especially one that's not meant to be reserviceable as the present generation ones are.
I can validate what Jason said, because actually I was the person who made the science case to lend this to NASA headquarters in the early 90s to buy into the Kecks. At that time, all we had in mind was using the Keck as interferometer to do imaging of disks, protoplanetary disks, High res was not on anyone's radar, and of course, high res has turned out to be the fantastic instrument it has been for Keck. So you're exactly right. A ground-based telescope, you don't have to send up a spacecraft with astronauts with wrenches. You just have to send a few guys up who are at ground level have written down on a piece of paper what they want to do, so they don't get into oxygen deprivation, and do it.
And I think that we all know that if we look in an unexplored region, we're likely to find things that we haven't anticipated. And we're going to find usually more things that we have not anticipated than things that were planned. I never met Barry, sadly, but someone put up a quote by him first day, something like, I never understood why going fishing is such a bad idea, because that's how you catch fish. And so I think we all strongly believe that. But somebody else put another slide that showed that the media attention to NASA failures is orders of magnitude greater than, and not just NASA, but any government project than successes. So I think that that generates a huge risk aversion that then makes you have to identify a science case, even if you know that more than 50% of the value of your project is going to come from things that you haven't anticipated. I'm not sure how to change that, other than somehow, give more leeway to government projects for failures and not kind of punish failures so much.
Jim.
Just a question, how many M stars can you look at with a 30-meter ground-based telescope and actually do direct imaging on their planet and habit?
I think there were, so we have a plot of this in the new GMT science case that we made. Then there's a histogram that actually counts them all up, and there's a ranking by how easy they are to do, but my memory is that it's a couple tens, 20, 30, depending on what you assume about the progression in ground-based coronagraph. We did a pessimistic case using present-day technology and an optimistic case.
But your inner working angle is pretty small.
Right.
Right, and the exoplanet demographics around M dwarfs are really quite favorable for lots of rocky planets. So having a few tens, it sounds like a low number, but that should translate to a few tens of rocky planets.
Does the new Meredith number on how often flares are and how powerful they are change the devolatilization models of M-star habitable planets?
We're going to be surprised, and that's why we're looking.
I mean, there are people who are coming up with clever ways to protect M-star planets. I don't know, is that what you wanted to say?
Well, we haven't even talked about what I think is the most serious problem for M-star planets, which is their pre-main sequence evolution. The M-star is 10 to 20 times brighter during its pre-main sequence phase than it is once it hits the main sequence. So these that pre-main sequence phase lasts hundreds of millions of years, whereas the planetary accretion time is millions of years. So, these planets are likely to be completely devolatilized before the star ever hits the main sequence.
So the clever geophysicists can find ways to store water in the mantle and have it outgas slowly so that you can protect a potentially habitable, volatility for a long time. We just don't know what really happens, right? We actually have to go measure some stuff.
Well, 2 weeks ago, somebody presented work on the density of several of the habitable planets in TRAPPIST-1, and they said the densities are consistent with being less dense than the Earth. So maybe some volatiles there, but I guess the error bars are quite big.
Yeah, that was this claim that there had to be some large component of water on the track as well because of the density.
Question back.
So it's not a question, it's just more of, I'm curious what the panel might think of it. A new technology is being looked at as to complement these large ground-based facilities and actually having an orbiting star shape that will actually work with ground-based facilities. So just curious what your thoughts are on things like this. It's a complementary technology of a star shape. It's going to be in orbit, it's also going to be serviceable, but also that your instrumentation, your actual spectrometers or cameras and everything will be on the ground and serviceable. So just curious what your perspective is from the panel or even just,
I actually brought along these slides from John Mather.
Yep, I have them as well. So.
because of the shortness of time, I did not load them, but that is a very serious proposal, yes, to fly a huge star shade geared to the ground-based USALTs. The main problem is we're not quite sure how to keep it over the telescope at the right time while Earth's rotating underneath. It could burn up an awful lot of fuel. And so that concept has been accepted as part of the so-called S5 star shade, the TRL level 5 technology development effort. They've gotten a chunk of money from NASA. It's being studied right now. I eventually will be part of a group that will oversee the effort of what they come up with. I've not been told yet that they're ready to present anything to us yet, but we are eagerly looking forward to see what they say they can do, because that's a brand new idea. It's really a John Mather out of the box Nobel Prize idea, and so it's got to be taken seriously. It's a good one.
Yeah.
So I haven't seen that one, but the studies that I have seen were rather pessimistic about this, and I guess the two reasons, although maybe there's some trick in this new idea that I think
they've got engineers studying it more and more seriously. So who knows? They may decide it's flawed.
Right, but my understanding is that, as Alan said, the fuel expenditures to keep something aligned with your telescope on the ground are just so great. And the second reason is that for the larger your telescope is, the larger your star shade has to be, and the farther away it has to be. And the distance, if I remember correctly, scales as the square of the aperture. So that scaling law is especially disfavorable for large telescopes.
So the concept I saw was it's not necessarily going to follow the telescope, it's more as a bit of occultation sort of an event.
I see.
So,
right. So then
it would just be whenever the star shape or the telescope happens to the
right.
path of the star shape.
Right. So the flux of an Earth-like planet, at 10 parsecs is something like 1 photon per 1 meter squared of aperture per minute, if I remember correctly. So now, if you have a large aperture, then maybe you can collect a few photons per second, but you do need to collect, for some time, even with a large aperture. So if you can keep it there for a minute, if that occultation for a minute, then I think you're in business. But less than a minute starts getting shaky, I think.
Okay, I think we need to turn it over to Jay at this point.
Yeah, let's thank our panel.